So, welcome students to the Zepto-certificate for the third lesson in this course about bioenergy and the role of biomass in the energy system. To obtain the certificate, you must first prove that you are aware of the different demands put on a fuel if it is aimed for a stationary applications or as a transport fuel, just to mention one thing. You must also have a brief idea about how different types of furnaces and boilers look, but only a brief idea. You shall be aware of the demands put on the fuel and energy carrier by the end product, and you shall prove that you are aware of the environmental impacts caused by combustion. To prove your capacity in these respects, you must first pass the test. The demand for a pass grading is 80% correct answers, and that there is also a 15 minutes time limit to meet. Your test result is sent automatically, and I will look at your report for the second part of the examination only if I have first received a message that you have passed the test. So see to that you pass the test first, and only when you have done so, then go on to the essay described in this recording. Once you have passed the test, you shall judge the feasibility of different fuels for two different processes. When you have done that, you shall also assume that both processes could be supplied using electricity as the energy carrier, and then you shall again judge how the different fuels fit. As shown in this slide, you shall finally describe your findings in a short essay, only some 3 to 5 pages, including a master table where you compile the data. It is important that your master table is easy to read, because you shall imagine that your essay is intended for a non-professional. Maybe you want to think that your essay is for an economist, or maybe you want to think that it is for a politician. Whichever, it is important to remember that this type of summary data for new projects often has to be presented to decision makers short of time and short of the detailed knowledge. So the information must be condensed and it must be very clear. In this slide you find the basic data for the two processes. As you will see, they both run continuously and they both demand a net thermal power of 5 megawatts. But the temperature requirements are different. The total efficiency in the different processes will really be a function of several parameters, but you shall use a simplified treatment. As you see from this slide, you will assume that the heat losses from the processes is split in two parts. The wall loss is constant in all three cases: glass melting, brick making, or electricity production. And this is a normal situation. 2% is a low number for small processes like this, but it is not unrealistic for well-insulated modern process furnaces. The heat loss through the hot flue gases is assumed to change in direct proportion to the change in fuel quality. And the fuel quality is measured as the ratio between the gas produced from the combustion of 1 kilo of fuel to the energy content per kilo of fuel. So the bigger the gas volume or the lower the heating value, the bigger the losses. You will see an example worked out in this slide. It is obvious that this treatment is very simplified, but it does give an idea of how things work. The fuels in this task originate from 3 different sources, and the elemental analysis with respect to carbon, hydrogen, nitrogen, sulfur, and oxygen will become different. So what you want to do is to find an analysis for the dry and ash-free substance. To do that, you will use the Phyllis database, and you will select a number of samples from this database to obtain a realistic mixture. In this slide, you will see which samples you shall select. As you see, the first category of fuel is a hardwood mixture. On the next slide, you will see how we can go about to assume this mixture to come from a forest felling operation. The second category of fuel represents park trimmings and prunings from fruit orchards. And the third category represents agricultural byproducts. The three different fuels are results from different types of operations, so the availability is different over the year. The first category of fuel, the forest residues, are produced and are available all year round. For the second category, park and orchard trimmings and prunings, they will be available only during 6 months per year. So this fuel fraction is produced only during the months April through September. That means that fuel must be stored for the remaining part of the year. For agricultural byproducts like straw, the seasonal production is ever more pronounced. So the straw is produced and must be collected only during 3 months, and then it must be stored to be available during the remaining 9 months of the year. The handling of the fuel at the harvesting site will have a strong influence on the ash content. A typical situation at forest fellings is first that the fuel fraction consists of thin material. That means that the fraction of bark relative to stem wood is high. It is also quite common that the fuel fraction falls on the ground and is collected from the ground. It is not unusual that the harvester drives across the fuel fraction, pressing it down into the soil. All these factors together tend to increase the ash content, and you shall use 8.15% ash content for the wood fuel. The same thing applies to park rinsings and orchard prunings. So even though the Phyllis average analysis indicates an ash content at less than 1%, you shall use 5% for this fraction. For the straw, you will use the ash content suggested by Phyllis, and then you will select the value measured at 550 degrees. So that is 6.77%. So now you understand why it was important to find the ultimate analysis for the dry and ash-free substance in the previous slide. The dry and ash-free analysis will be connected to the species involved. It will have a connection to the biology and to the raw materials. But the ash content will reflect the handling during harvesting. If the fuel fraction is handled with care, then the ash content may be as low as the average values in the Phyllis indicate. But if the handling of the fuel fraction is careless, then will the ash content increase. And there is one more aspect to the fuel quality, and that is the moisture content. The ultimate analysis of the dry and ash-free substance represents and reflects the biological origin of the material. The ash content reflects the handling at the harvesting site, and the moisture content reflects the supply chain. If the fuel is transported green, that is, it's taken from the harvesting site straight to the energy plant, then will the moisture content be that of the living cells. So during some seasons it may be 60%, while other seasons may see a fuel at only 40% moisture. So you will assume 50% for one assortment of the fuel. When the fuel has such a high moisture content, the combustion process will become more difficult. So at a high moisture content, you will usually have to use an increased amount of air. So for all three fuel origins, you should use a lambda equal to 1.25 when the moisture content is 50%. Then, if the fuel supply chain is delayed, then there may be time for intermediate storage in windrows. You will read about that in text section 317 in the Busy Plan Handbook. Using open-air drying in the way described in that text section, you may achieve a moisture content as low as 25%, depending, of course, on weather and climate. For agricultural fuels, this type of handling may be difficult because they tend to deteriorate, but for woody fuels this is a common way. The delayed delivery means that there is a capital cost involved, so the fuel becomes a bit more expensive, but since the moisture content is lower and generally less variable than with a direct transport, then the quality is higher. For the treatment in this task, you will assume a 30% moisture to represent this type of delayed delivery. This is a reasonably low moisture content, and a good combustion chamber should be able to perform well at an air excess factor of 1.2. Finally, and the third way to organize the supply chain, the fuel may be dried. Drying down to moisture contents below 20% requires forced drying. Anyway, that is the case in all practical situations. So this is an expensive way of handling. But the dry fuel can then be pelletized to save transport cost, or it can be milled to be used in pulverized fuel burners. So there may be things to be gained by the expensive drying process. So this is the third supply chain you shall include in your calculations. You will use 10% moisture content to represent this case. Again, the low moisture content allows for a low excess air, and you shall use 1.2 in your calculations of the combustion process and the efficiency. To summarize the data so far, in total you have 9 different fuel qualities. There are 3 different origins of the fuel: hardwood felling residues, park trimmings and fruit orchard prunings, and straw and agricultural byproducts. And there are 3 different moisture contents representing 3 different supply chains. And then you have 3 different processes. The glass melting furnace requires the temperature to exceed 1500 degrees C, and it requires a net power at 5 megawatt. So if the total efficiency would be only 90.9%, then the power supplied by the fuel would have to be 5.5 megawatt to cover the losses. And if the total efficiency was as low as 83.3%, then would the supplied power from the fuel have to be 6 megawatt. The same reasoning applies to the building brick process furnace. Like for the glass furnace, is the process requirement 5 megawatt net, but for this process is the temperature demand only a modest 1100 degrees C. The third process you shall account for is electricity production. The temperature demands for electricity production are extremely low, so that is not a limiting factor. To supply the building brick process and the glass melting furnace, you will have to deliver a total of 10.2 megawatt electricity. The 0.2 megawatts will cover the wall losses. But with electric heating, there are no flue gas losses from the final process. On the other hand, will the electricity efficiency be limited by the Carnot limit? So for the electricity production, the third case, the minimum fuel input will be equal to the electricity delivery, 10.2 megawatt, divided by the Carnot efficiency. Just assume the Carnot efficiency at 50% and assume the desired electricity output at 10.2 megawatts. Then the fuel input must be at the very least 20.4 megawatts. And then comes the wall losses and the flue gas losses in the combustion chamber where the steam is raised, so in the steam boiler. So if we have the wall losses at 2% and the flue gas losses 5%, then the total efficiency in the combustion process and the boiler is 93%. So then the total fuel input becomes 20.4 megawatts divided by 0.93, which is 22 megawatts. But you should of course calculate the Carnot efficiency from the actual process temperatures, and also the combustion efficiencies should be the ones that you have calculated for your cases. In this case, for the electricity production, the high temperature in the steam cycle is 580 degrees C and the low temperature is 15 degrees C. So what you want to do is to make use of the computational tools that you have already developed during this lesson. First, you want to compute the heating values, the amounts of combustion gas, and the adiabatic temperatures for all the fuels. Doing this, do not forget that the excess air factors will reflect the moisture content to some extent, so they will be different. Then you will use the data so obtained to estimate the total efficiency in the combustion process. In the case of electricity production, there will be one more efficiency to take into account in the final calculation, and that is the Carnot efficiency. So compute that value too. There will be some combinations of fuel quality and process demands that simply do not work. So exclude these cases from the forthcoming calculations. And then use your data to compute the necessary fuel input as expressed in megawatts for each one of the remaining processes. Convert the result from megawatts to tons per year. And then, when you have these numbers, you will take the seasonability of the park and orchard trimmings into account, together with the seasonal variation and availability of the agricultural fuel fraction. And that will give you an input to think about how much has to be stored and so on. And these things shall all be presented in a short report. So good luck to you all, and let me say that I look forward to reading your essays.